Good morning, linear algebra. Well, it's morning for me. I don't know when you'll be watching this. I just wanted to go over a couple of ideas that are related to the dot plot product exploration that you just did and show you a couple cool things. So the first is this is Yashin's amazing picture that has to do with the application of dot product related to work. A few of you had questions about 14 and 15. So I want to talk about those really quick. So Yashin's drawing is really great. So this child is pulling the wagon 55 degrees and it's moving horizontally. So the work done by the child is the distance that it moves. So that'll actually be the magnitude of this moving direction vector. And then it's the distance that it moves times the force in that direction. So we're multiplying the length of this and the x component of the force vector. So what we first have to calculate is this x component. So let me just show you this picture. So the work done is this length times the distance moved. So if you remember trig, this length is just f times cosine of theta, where f is actually the length of this vector, not the vector itself. So this is magnitude of the vector f times cosine of theta, and then we multiply that by magnitude of the vector r. So if you end up with magnitude f times magnitude r times cosine theta, that is actually the dot product of the f vector with the r vector. So let's see if Yashin has gotten hers to be written correctly here. Not quite. That's okay. So this work formula is just going to be f dotted with s, because this is the geometric definition of dot product. So I hope that clarifies it just a little bit. And then the other thing, maybe here, she got the magnitude of f times the magnitude of s times cosine of the angle. This is just vector f dot vector s. So a really easy way to write work is just f dot s. Perfect. So now the other thing I want to show you is a really cool way that Huang did his proofs for the different properties of the dot product. So this is how I did my proofs, just writing everything in terms of the coordinates. And Huang did that too, but his first version up here is actually totally valid. The definition of dot product is the transpose of the first vector times the second vector, thinking of that as matrix multiplication. And because of properties of transpose, we could actually do these proofs given what we know about matrix multiplication and transposes. So A plus B transpose is A transpose plus B transpose, and if we multiply that by C, we get A transpose C plus B transpose C, which is A dot C plus B dot C. So that immediately finishes the proof for us. We don't even have to do this step. So I thought that was really neat, and I wanted to share it with you guys as well. So let me know if you have any other questions about this activity, and I will post solutions to section 6.1 problems at the end of the week. Great, good luck.